All right, I think we'll get started. All right, so before we get into I guess we'll have our first YouTube Friday today. So we'll look at some videos of some interesting fluid behaviors. But first, we have just a little bit more ground to cover, just to make sense of what we're going to see in those videos. And an announcement. This comes from Tony Butterfield, who's putting together the Student Advisory Committee, and asked me to show this to you. And you also saw there was an announcement that I posted to Canvas about nominations. So please, if you haven't already, either follow the link here in these slides that have been posted, or on the announcement to Canvas, and nominate yourself or someone else who you think would be a great representative for your class. And note that there will be 4 or 5 members of the Student Advisory Committee, and that's to make sure that there's representation of transfer students as well, right? So if so there's a representative from freshman, sophomore, junior, senior class years, and then if there are no transfer students among that group of 4, then there will be 1 additional SAC member from transfer students. So please nominate yourself and your peers. And then on September 9th, we'll have the nominees actually just give a brief introduction to themselves and pitch for why you should vote for them in class just before we get started. So about a minute or so per nominee. Any questions on this? You've all done this before, right? Or many of you have done this before, right? For sophomore year, freshman year? No? Oh, okay. I just assumed you had. Maybe this is new. Maybe this is new as Tony Butterfield has taken over for Jeff. Okay, well, anyway, so this is new this year, and that's how we're going to do it. All right. One more announcement. Your other TA, who I guess you hadn't met in person yet, is Rob. So Rob is sitting there in the front. Yeah, wave. Rob is going to be hosting TA office hours. Yeah, so Tuesday 4 to 5, Wednesday 1:30 to 2:30. So you'll be the last person to see them just before the homework is due. I guess Adriana, maybe anyway, look at the office hours schedule on the campus page. But thank you, Rob. I think Rob has to take off. Okay. So like I said, just a few things to get through before we get to a few videos showing some interesting fluid behaviors. But just to recap where we were, right? So we were using the definition of a Newtonian fluid. So we said, if this is a Newtonian viscous fluid between 2 flat plates, and we want to know what is the force required to move this upper plate, we've had to find the velocity profile in the center here, and we found that because this is it's a constant force that's being applied that has to happen in order to keep the plate from accelerating continually. And the plate has to be moving at a constant velocity as well. So we ended up with a linear velocity profile for this case of a moving flat plate above a stationary plate, where we had U is V times Y over H. And then from this we can find the applied shear stress. So that's the force per area of the plate required to keep the plate moving, as tau is equal to mu times du dy. And if we look at the gradient in velocity, right, so if we just take du dy, right, so du, derivative of u with respect to y, we'll get v over h. And so tau, the applied shear stress, is just mu, right, our Newtonian viscosity, also like that constant of proportionality between shear stress and velocity gradient, times v over h, right, times du dy. Okay, so that's where we ended up, or just about got to at the end of last class, right? And so this is, and this comes from the definition of a Newtonian fluid. So if we look at this property of viscosity, right, this is going to be really important when we're dealing with understanding how applied forces interact with fluids. It's going to be one of the key properties that we'll see over and over again. We can ask, like how does fluid viscosity change with pressure and temperature? So this is a plot that's kind of an approximate, gives you an approximate estimate of fluid viscosity for essentially any fluid relative to the critical point properties. It's only good to within maybe 20% or so. So it's not a great estimate. You want to use a table, don't use this. But this can show us the behaviors that we see though, as a function of temperature and pressure, and that's why we have it here, not as a reference. And so what we can see is that viscosity in general is a strong function of temperature, right? So we see, these lines of viscosity at constant pressure have, in general, a strong relationship or a strong change with temperature. But we see that these lines, at least in many of the regions on this plot, these lines of viscosity at constant pressure are pretty close together, indicating that in general, viscosity is a weak function of pressure. So what this tells us, practically speaking, is that the temperature dependence of viscosity is something that we may have to pay attention to, but we don't really have to pay so much attention to a dependence on pressure for a Newtonian fluid. And this can be significant, right? So if you run a set of experiments in the lab and it's 25 degrees C in the lab one day because the air conditioning is out or something, and then the next day the temperature is 19 degrees C, you could actually see substantial difference in your results because of this dependence of viscosity on temperature. Same thing if we had water or oil or something flowing through a pipeline. There is a strong dependence on temperature of viscosity. So we've been talking about Newtonian fluids, examples of Newtonian fluids. I don't know if I realized based on a question at the end of class on Wednesday. I don't know if we really gave examples of Newtonian fluids. Does anyone have an example or know what Newtonian fluid, or can give me an example of a common Newtonian fluid? Water, air, oil. So basically the common fluids that we're going to deal with in this class are Newtonian fluids, which is why we talked about this Newtonian fluid model. And for the rest of this class, we'll talk about non-Newtonian fluids on this next slide and sort of definitions of non-Newtonian fluids. But as we're doing analysis, we're going to basically restrict ourselves to Newtonian fluids from here on out. But it's still worth discussing what non-Newtonian fluids are. So basically, not all fluids obey a linear relationship between shear stress and velocity gradient, like we assumed for a Newtonian fluid. And so this is a plot of how shear stress changes with the rate of strain, or the rate at which we are deforming a fluid element. And remember, in a Newtonian fluid, we assumed that the shear stress, tau, was proportional to d theta dt, proportional to the rate at which we shear a fluid element. So what's the slope of this line for a Newtonian fluid? What is the slope? Mu. I heard mu. Yeah, mu. The viscosity is the slope of this line for a Newtonian fluid. And so, but not all fluids exhibit this kind of nice relationship. So some have this curve get steeper. And remember, the slope of this line is like the viscosity. And so that's effectively if the slope is getting higher, that's effectively the viscosity getting higher. And other fluids, like pseudoplastic fluid, have the viscosity get less steep, right? The slope get less steep, the viscosity get lower as we apply a faster strain rate. And so in general, something that doesn't obey this nice, neat linear relationship is called a non-Newtonian fluid. So Newtonian examples would be like water and air. Shear thickening or dilating. Example here would be like oobleck or quicksand. And we'll watch this video in a few minutes. So these are fluids where, so shear thickening, meaning it effectively becomes thicker or has a higher viscosity when you apply shear stress to it. And we'll see, yeah, again, examples of that. The opposite behavior is shear thinning or pseudoplastic. That's this line down here. And those are fluids that actually become essentially less viscous as they start to flow. So a good example here is paint, right? So can anyone tell me why we might want this behavior with paint? So shear thinning fluid means that when it's sitting there, right, when there's no shear applied, it has a relatively high viscosity. But when you start applying a shear, the viscosity drops. So if we're putting paint on a wall, why would that be a good behavior? So yeah. Easy to spread, but it'll stick to the wall. Exactly, right? So if you're putting paint on a wall, you want it to stay there, right? So you want it to behave like high viscosity, like honey or something, right? When it's on the wall and you're letting it dry, but you still want to be able to brush it out. And so this kind of behavior, pseudoplastic shear thinning behavior, is exactly what you want in paint. So there are other material models. So one shown here is Bingham plastic, so like ketchup. So it's a material that behaves almost like a solid up until some critical stress is applied, and then it starts to flow. And we typically model it as something like a solid and then something like a Newtonian fluid. So we see a straight line up there for Bingham plastic. An example here would be ketchup, right? So if you have ketchup in the bottle, and you shake and shake and shake and it doesn't move at all, then all of a sudden the whole thing glumps out. That's when you've reached that critical yield stress, all of a sudden it starts to flow, and then the whole, if you make a big mess all over your French fries or whatever. So that's a Bingham plastic. But it gets way more complicated than this, and we'll look at some examples of this in videos. But for example, non-Newtonian viscosity can also be a function of time. So like lead or asphalt, like asphalt is actually on a long enough time scale behaves like a fluid, even though we think of it as a solid. An example is the longest running, I believe one of the longest continuously running experiments in the world, still running right now, is the pitch drop experiment. And so basically, it's well over 100 years ago, someone placed a glass vial, took a glass vial, filled it with pitch, which is like resin from a tree. And it basically it looks like a solid material, right? You can like pick up a chunk of this stuff with your hand. And then they cut off the bottom of this vial. So there's like a little like neck opening, and they cut open the bottom of the vial and then let it sit and watched it. And there have been something like, I don't know, less than 10 drops in over 100 years that have collected and formed out of the bottom of this vial, because this thing is flowing, but it's flowing on a time scale that is, just very, very, very long. So we are not going to watch a video of the pitch drop experiment. That would be way, way too long. So that you all can view this later. Okay. All right. Well, hopefully on Monday. So now, as promised, we're going to move on to chapter 2. And in chapter 2, we're going to be talking about fluid statics, right? So remember, we think of fluid mechanics as being both the behavior. So fluid mechanics broadly is the behavior of fluids in response to forces, applied forces. Many times that force will result in motion, like in, for example, that flat plate example. We've already done some fluid dynamics in chapter 1. But before we start really talking about what happens to fluids in motion in detail, we're going to start by talking about static fluids and pressure distributions in static fluids. And so here we're going to be primarily concerned with fluid pressure. And fluid pressure is one of the ways that that fluids respond to forces. So this is an image of a submarine, right, which is under enormous pressure from being underneath the sea. And by convention, we are going to define pressure to be positive for compression, right? So when we get to the bottom of the Marianas Trench or something, there is an enormous amount of pressure pushing inwards onto a submarine or submersible vehicle, right? If you go to the bottom of a pool to get a diving ring or something, you feel a pressure inwards on your eardrums, right? And this is, so by convention meaning an arbitrary choice that we all stick to. We'll see, actually, it's maybe not the most natural choice for the math. So when we start doing derivations of what's going on with, you know, and just trying to describe how fluids respond to forces, we're going to see that this convention, which makes intuitive sense, right? We think of pressure being, you know, higher when we're getting pressed inwards, right? It's just kind of like the derivation of where the word comes from. But it's actually going to mean we're going to have a negative sign oftentimes sticking around in our equations in front of the pressure term. So that's why I highlight this. So be careful about that. Yeah, so the way to think of this, water pressure in the ocean presses inwards, compresses a submarine. Right? All right, so we didn't get that nice little break to view the YouTube videos. So we'll use this as a way to maybe wake everyone up. What I want you to do is get into groups, and very quickly, I have, you know, about a minute, it'll probably be a little bit longer than that. Get into groups of 2 to 3. And what I want is just some ideas. We haven't really talked that much about forces and fluids yet, but just some ideas that you have about what can create pressure in a fluid element. What kinds of forces, what kinds of phenomenon, what kinds of things do you think might be able to create pressure in a fluid element? Just any ideas you have, okay? So 2 to 3 minutes, please discuss, or 1 minute. All right, I guess we'll call it there. This is going to be pretty quick. Just getting everyone to talk. Wake up a little bit, right? Just wake up a little bit. All right, who has an example for me? It'd be nice to do this morning. I'm not going to call on someone. Yep. Hydraulic press. Yeah. So hydraulic press can definitely apply pressure to a fluid. More generally, right, a surface, right? We can apply pressure to a fluid by confinement, or by pressing on it, or by moving a surface, right? Yeah, but that's a good example. Yeah. Do you have another example, or were you going to say? I was to say heat. Yeah. So we can change the pressure of a fluid, particularly a gas, with heat. Yeah, we will likely leave that. I'm not even sure it's going to make my list of ways to apply pressure to a fluid here, but we can definitely apply pressure with heat. Yep. Gravitational forces? Gravitational forces, definitely. That's going to be the main thing that we're going to spend our time talking about over the next couple of slides. So if you've been looking ahead, that's definitely up there. No, that's good. Yep. Would intermolecular forces cause pressure? I mean, intermolecular forces in the sense of the molecules bouncing around, right? That would be like a molecular origin of pressure. But generally, in a fluid, we think of intermolecular forces as actually causing viscosity. We've kind of alluded to this actually by explaining in our discussion of what non-Newtonian fluids are and how, like, why it's shear thickening or shear thinning. But we can think of viscosity as being as arising because of intermolecular friction, right? So if we have the parallel flat plates example, right? We have one plate moving over the top of another. So if we consider, someplace within the fluid between those two flat plates, the fluid on top, right, let's say is moving faster than the fluid on bottom. That means the molecules, let's say it's water, the molecules of water are moving faster, right, but they're being resisted. They're feeling a resistance from the slower moving molecules underneath because of intermolecular interactions between them. And so that viscosity is rising because of all of those intermolecular interactions. And we measure it as this like bulk property of viscosity, but it's actually being caused by intermolecular interactions. So I'll give kind of intermolecular interactions, but that's definitely where viscosity comes from. Any other ideas for pressure? Yeah. Adding more molecules to a given space in a compressible fluid for sure. Then we will have, and adding more molecules will give us more pressure. We're going to spend most of this class ignoring that effect though, right? So we're going to spend most of this class saying that the number of molecules in a given area, basically, or the density of the fluid is constant. So we're going to spend most of this class assuming incompressible fluids, and then we're going to talk about compressible fluids at the very end. Yeah, but that will definitely come up. Other ideas? Yeah, sure. That's correct. We'll do a derivation that'll show us why that's true. But that's a really good question, right? Because we think of pressure. So one way to think of what's called hydrostatic pressure, and we'll talk about this in more mathy terms, but hydrostatic pressure is basically the pressure of the fluid column above you, right? So we're at a little bit less than 1 atmosphere of pressure because we're at elevation here in Salt Lake City. And that pressure that we feel, that atmospheric pressure that we feel, we can think of it as being due to the weight of the column of air that is above us and that is being pulled down by gravity on top of us. And when you're in a pool, a swimming pool, or underneath the ocean, you have not only the weight of all the air in the atmosphere above you, but the weight of all the water that's above you as well. All right, and that's definitely pressing down from above. But we'll see that because of the nature of pressure as a force that's acting inwards on the surface of fluid elements, if we have a pressure that's coming down on us, right, pressing down, it's also pressing equally at a given location, pressing equally on us from the sides and even from the bottom on a fluid element. So we'll see that pressure is going to be a point property of a fluid that is acting inwards in all directions. Okay, but we'll see. We'll do a little bit of math to show that that's true. Actually, in just a few slides. Yeah. Yeah. So changing the volume which it's in, right, for a compressible fluid, is another way to change the pressure as well. Okay. Let's see what I have on my list. So fluid weight, gravity, right? That's a big one that we're going to spend a lot of time talking about. Surface tension is a way of changing the pressure within a fluid, and we'll look at some examples of that as well. So surface tension, actually, ordinarily we would have seen a video by now on surface tension, so maybe that would have come up more. But surface tension is like the intermolecular forces, or the effect of intermolecular forces at the surface of, for example, a fluid. Fluid motion can cause pressure. So in this chapter, we're going to consider fluids to be static. But in future chapters, we're going to see how the motion of a fluid can actually give rise to a pressure. And if you've ever, ridden a bicycle and felt the wind on your face, right? Felt the pressure of the wind on your face, or honestly just been outside on a windy day and felt the pressure of the wind, you've felt this effect, right? Where the motion of the air, which is a fluid, striking your face or your hand, gives rise to a pressure when it slows down upon hitting your face. Boundary motion, right, like a hydraulic press, or like a flat plate, or a flat plate in combination with something more complicated could give rise to an internal pressure. Acceleration can cause pressures, and just sort of other So, if we, in certain cases, if we apply electric fields to fluids, we can actually give rise to pressures within them. Especially in micro and nano channels, and this was basically the subject of my PhD thesis, was on how electric fields interact with fluids in micro and nano channels. But in this class, we're going to start with these first two: gravity and surface tension. So fluid weight and surface tension. Motion, like fluid motion, boundary motion, a little bit about acceleration. We'll talk about that in sort of the rest of the class. All right, so as a means of answering your question, we're going to look at a fluid element. Does everyone know what I mean by a fluid element? We've talked a lot about them. What do I mean by a fluid element? Like a very small chunk of fluid. That's what a fluid element is, right? It doesn't have to be next to a boundary, right? So in the last section, we considered a fluid element where one side was moving faster than the other, right? To talk about shear stress. So it can just be a fluid element that is just sitting, like a little tiny parcel of fluid that's sitting in the middle of the fluid itself. So if we consider a fluid element in equilibrium at rest, so no motion, and therefore the velocity is zero, so there's no shear stress. So the net force on this fluid element is zero, right? We can do a force balance on this fluid element to learn something about pressure. And we're going to assume that there is nevertheless some pressure, some unknown px, pz, and this, we're going to call this pn, acting on this fluid element. And remember, the pressure is defined as positive inwards by convention. So we're drawing all of these things as acting inwards on this little triangular fluid element. And pressure acts normal to the surface of a fluid element as well. So it's a normal acting inwards force. So we have drawn these vectors as pointing inwards in all directions. And we're going to also allow this little fluid element to have some weight. And we're going to factor that in as well, right? So there's a gravitational force, gravitational body force on this fluid element, as well as the pressure force. But this whole thing is in equilibrium, right? It's like a little piece of fluid element sitting in a static pool, say, of water. So we're going to first consider the sum of the forces in the x. So we know sum of forces in x is zero, because the fluid element is at rest, right? It's at equilibrium. And that's going to be the pressure in the x direction, and pressure is a force per unit area. And so we're going to take the pressure here and multiply it by the area of the fluid element. So it's going to be this delta z times whatever the width is into the paper. We're calling it width b. So we have px b delta z, right? Is the pressure, is the force being exerted by this pressure in the x direction. And it's positive, right? Because we're in positive x direction. And it's opposed by the sort of x component of this pressure force. And we can write that as Pn times B delta S, right? So again, that's the area of this fluid element. And the component of it in the x direction, which is what we care about, is this sine theta. Okay. And the weight is acting down, so we don't have to worry about the weight of the fluid element here. So we just have force in this direction and the x component of the force being exerted on that triangular face. But we can write this delta S sine theta is equal to delta Z. If we do a little bit of trigonometry. All right, sine theta would be delta S over delta Z. So delta S sine theta is equal to delta Z. And so we can simplify this, right, and say sum of the forces, which is zero, is Px b delta Z, same term, minus Pn b delta Z. Right, but now if we drop out those b delta z's, we see that this is equal to zero. This is telling us that Px is equal to Pn. All right, so the pressure here is the same as the pressure here. All right, so Px is equal to Pn. So now we're going to do the same thing in the z direction. Right? So in the z direction, now we're going to account for gravity. So this element is a finite size. So we're gonna allow this fluid element to have weight. And we have essentially the same idea, right? So we have pz b delta x. So that's the force upwards in z from the pressure. We have the z component of the pressure on that triangular face. And then we also have the fluid element, which is pulling it downwards. Again, we can do some trigonometry to resolve that. We end up with this expression here. And now we have pz is pn plus 1/2 rho g delta z. But now and that's true if we have a finite size fluid element. But now if we take the limit of this fluid element getting smaller and smaller and smaller, if you notice here, there's no delta term in this pz. There's no delta here, but there is a delta z here. So if we take the limit of this fluid element getting smaller and smaller and smaller and smaller and shrinking all the way to just a point in space, right? Just a tiny, tiny, tiny fluid element, infinitesimally small fluid element, delta z is 0. Then we end up with the result that pz is equal to pn, because this would drop out. And therefore we end up with pn is equal to px is equal to pz. If we did this in y, we would get is equal to py as well. So this is telling us the pressure is a point property of, that tells us what's going on in the fluid at an individual point, right? And the pressure and so if I'm sitting here underneath the column of fluid above me, and I'm feeling pressure from the weight of all of that fluid above me, right? That's pz, but I'm feeling that same pressure inwards in x and y that I'm feeling in z. And in fact, if I have a fluid element sitting here, infinitesimal fluid element here, it's feeling the same inwards pressure in all directions. Okay. Yeah. This is true even if this is actually true even if the element is moving. So the pressure is a point property. So we talked about so one important implication here is we talked about velocity on the first day as being a vector field, right? There's a vx, a vy, a vz in 3 dimensions, right? This is telling us that there's just a p, there's just a pressure. It is not a vector field, it is a scalar field. Yeah. Okay. It is a scalar field, not a vector field. Okay. Yeah.
So modeling this is just a point at what scale is that applying?
So for modeling, we are. So if we had, so remember, we're treating a fluid as a continuum, right? So we're treating it as a continuum of points. And so we're going to then, so what this means is that we are going to, when we're solving a fluid problem, we're going to be solving for like the continuous variation of pressure within the fluid due to motion or due to gravity or whatever other forces are being applied. So we're going to say that like pressure, we're going to look at how pressure is a function of z. So we'll see how pressure changes with variation in z. But at any given infinitesimal mathematically tiny point, we're going to say the pressure is the same in all directions. That makes sense. So we'll see. So we'll see that in the z direction. So for example, in a fluid that is under the effect of gravity, we'll see that the pressure in z, the pressure in general increases as we move downwards within that fluid. But at any given point, the pressure is exerted in all directions on a fluid element. Does that make sense? So if it's not infinitesimal, then in general, it may vary across the size of the fluid element. Okay. If it's not infinitesimal, it can vary across that fluid element. Yeah. Yeah, yeah, we'll talk about where this comes from, but yeah, it's a weird effect that no matter how wide the container is, at a given depth within the fluid, we're going to have the same hydrostatic pressure, even if it's a weirdly shaped container. And we're going to see, actually, hopefully next week we'll see a video about that, but maybe not. Yeah. Sorry, it's not necessarily, it's not that pressure is just one value throughout the entire fluid necessarily. It's just that at a given point, the pressure being exerted in the x direction is the same as the pressure being exerted inwards in the z direction and the y direction. That's really what's happening. So pressure can still be a function of x, y, and z within the fluid. So it can still vary as we move around within the fluid. But at a given point, we're just saying that the x component is the same as the y component, is the same as the z component, meaning it is not a vector, it is a scalar. It's a point property like temperature, right? The temperature, right, doesn't have an x, y, or z component. Neither does pressure. That's what this is saying. That's really what we've gotten to here. So we've learned a few things from this. So for all fluids, pressure is a point property independent of orientation. So it's not a vector, it's a scalar. In general, it can still be a function of space and time, right? So it can still be a function of x, y, z, and even time, right? If we have the fluid moving in time. But it's just that there is just a single value of the pressure at every point within the fluid, not multiple components in x, y, and z. Does that make sense? I feel like that's a point of confusion. Like temperature, think like temperature, right? Temperature is a point property, a scalar property, but it can vary, right? Within the room, if we're next to the vent, we're going to see, a lower temperature, right, with air conditioning being on than we will, over in another corner of the room. And the same thing with pressure. Pressure can vary with location and time, but just doesn't have different x, y, and z components. For fluid at rest, we said that there's no pressure change. So another thing we see here, if we consider the fluid element to have some size, we saw that there's no pressure change in the horizontal direction for this fluid at rest. But in the vertical direction, the change in pressure is related to the change in height. And we're going to develop this further to talk about hydrostatic fluids. All right. And so we're going to end there and pick up hopefully with some videos to explain some things on Monday. All right. Thank you all.